This is the first video in a series of 33 regarding concrete slabs. At the end of this video, you will understand the load transfer of one-way slabs. The overall use of concrete in an office building, you can easily see that 60% of the total concrete volume will be for slabs, 20% for foundations, and another 10% for columns and walls. A slab is a member for which the minimum panel dimension is not less than 5 times the overall slab thickness. Take a volume of concrete and order the dimensions by magnitude. The biggest is L and the smallest is H. When the main load panel is L times B, then we call this volume of concrete a slab if the length is bigger than 5 times the depth, H, and the width is at least larger than 5 times the depth of the volume. When the main load panel is H times B, which is this one, then we talk about a column if the width is smaller than 4 times the depth, and it's a wall if the width is larger than 4 times the depth. So the choice if a volume of concrete is a slab, a column, a wall, or a beam is not judged by yourself, but it has a definition within the code. And for each type of volume, there are different rules to calculate reinforced concrete. A slab is a volume of concrete, and there are two items that's applicable. This is thinness and flatness. Thinness means that one dimension is much smaller than the others, and flatness is that the center plane is a plane. So you have a sheet type of concrete volume. In this course, for the slabs, we will not consider loads in the plane directly in the plane like it's mentioned here, but we will only consider loads which are perpendicular to the slab plane. You can have different type of slabs, and I will give an overview of all the types that can exist, and I make reference to the drawings of Mr. Goodchild. The first one is a very typical one. It's just a concrete slab poured on beams and columns. You can minimize the concrete consumption like it is mentioned here in the second drawing. You can also use flat beams instead of the normal beams. This is to increase the free height under the slab. Then you can make a combination of the two. You can also use a grid of beams. This is always the case for two-way slabs instead of one-way slab. You can gain some concrete volume by making a waffle. You can also have plain concrete slabs. This is without beams. Or you can have some reinforcement on top of the columns. You can have slabs existing of precast elements. It can be a hollow core slab, pre-tensioned or not. Then the beams can be underneath the slab or above. You can have all kinds of combinations of the waffled slab together with the beams which are integrated in the slab, or even a combination like here. There are some rules of thumb. If you want to make a pre-design of a slab, then you can use those figures that I'm going to mention now. If you have reinforced concrete one-way slab, then you can go up to a span of 6 meters. And as first ID, you use a depth of the span divided by 20. For a reinforced concrete in a two-way slab, you can go up to 7 meters and you can lower the depth up to L divided by 25. For the pre-tensioned hollow slabs, you can go up to 15 meters and the depth that you need is L over 35. And then at last but not least, when you have the TT slabs, which is for very low loaded slabs, for instance a roof, then you can go up to 22 meters and a thickness, you need a thickness of L over 30. Now let's talk about structure and load transfer. A slab subjected to dominantly uniformly distributed loads may be considered to be a one-way slab of one-way spanning if, and there are two conditions, it possesses two free, unsupported, and sensibly parallel edges. So it has two parallel edges or two free edges, or it is the central part of a sensible rectangular slab supported on four edges with a ratio of the longer to the shorter span greater than 2. So if you have the two dimensions of a slab in a rectangular and one dimension is more than 2 times the other dimension, then we can cover this slab in one-way slabs. Regarding load transfer, a slab is suitable for uniformly distributed loads, and a slab is not suitable for line loads or for point loads. Of course, small line loads like light dividing walls or things like that, this can be accommodated, no problem. And we talk about small line loads if the load is less than 5 kilonewton per meter. Now let's see if this is true. When we take a rectangular slab, which is supported on this side and on the other side, simply supported, we make a uniformly distributed load. And then you see those lines in the different colors are the ISO lines of equal bending moments. These are the bending moments. And then you will see that the maximum bending moment is in the middle and it's about 14.7 kilonewton meter per meter. So this is a one-way slab with uniform distributed load. If you look at the bending moment in the other direction with the same slab, then you will see that it's almost zero. So there's no load transfer in this direction. So that's why we call it a one-way slab. We take the same slab, but now we take the sides not perpendicular to each other, not parallel to each other, sorry. So they are skew in a certain way. This and this one is converging and this one is also converging. We take the same load and the same distance as span, then you will see that there is some other bending moment lines and the maximum is 12.9 kilonewton per meter. But if we look at the bending moment in the y direction, now you have a total different picture. This are the bending moments in the y direction, and you see that there is a more significant bending moment in the y direction. We can now look at the summary of those two. If you take the first one with the non-parallel sides, support lines, then you will see that the bending moment in the second direction, in the y direction, is almost 30% of the bending moment in the x direction. When we have a one-way slab, like this one, then we will see that it is only 10%. The bending moments in the y direction is only 10% of the bending moment in the x direction. Now, in principle, the bending moments in the y directions is zero in this slab. But this program, this finite element program, shows some bending moment in this direction due to the program itself, due to the finite elements. A simple structure, plan view, 5 meters to 2 meters, but it's skew. It's not rectangular, it's skew. If you want to make this slab as one-way slabs, then you have to put it also in this direction, parallel to one of the sides, of the shortest side, parallel to the shortest side. Now you can use one-way slabs for this type of slab. When A is bigger than 2B, you make it a one-way slab. Some people think, yeah, let's take the shortest distance and let's put the slabs in this direction, but this is not a very good idea. If you do that, it's not a one-way slab. Once you arrive at the corner, you have torsional bending moments, which makes that your slab is not carrying off the loads in one direction. This is a plan view of a building, 33 meters long, 6 meters there, and it has a L shape. And we want to use one-way slabs because it's cheaper. It can be hollow core slabs, or it can be precasted slabs and partially precasted slabs. Then we can find a solution by making one beam here, and then this area, you can easily see that this proportion to that is bigger than 2, so we can use one-way slabs like that. And on the other side, the same thing, we use one-way slabs like that. So our problem is solved, but what's happening here in this corner? Well, in this corner you have the beam. These are, for instance, the hollow core slabs arriving from there to there on the beam, and this on the side, on this side, the hollow core slabs, they are from this side to this side. You see that in reality you have a joint here. It's not always preferred to have a joint here, so this is a disadvantage. In practice, when you have, for instance, a wide slab, precast with lost shuttering, then you can make this continuous. So in this corner, it will not be purely one-way slab, but we solve it by putting some reinforcement on the top of it. Looking at the bending moments, at the isolines of bending moments, it says a lot about the behavior of the structure. Now, if we look at a plot of mx, this is the x-axis, and we look at a plot of mx, then we see a figure like that. When we look at the plot of my, then we see almost a similar appearance. If you want to know now what are the support conditions, then you see with a thing, with a figure like that, then we look at the torsional bending moments, mxy, and you have a typical shape like that in the corner. Then we know that if you take all those three into account, then you will know this is symmetric, those two, and these are the torsional bending moments. Then you know that it is simply supported on all sides. Let's take another example. Mx has a moment distribution like it is mentioned here. You will see this is a hogging bending moment, and this is a sagging bending moment. So you will see, and there's no bending moment on this and this side. If you take my, it's just the opposite. Hogging, sagging, hogging. And when we look now at the torsional bending moments, they are nice, round, circular isolines without touching the sides. Then we know, if you look at those three together, it's simple, then you know it's clamped on all sides. It's fixed, on all sides. Another example, if you look at the bending moment in the X direction, then you see here sagging bending moment, no hogging bending moments. And Y, you only see on one side the sagging bending moments, this on this side here. And then on the torsional bending moments, you see again this shape of isolines and the same there, but not in this corner and not in this corner, only in this and this corner. Then you take those three together, then you will see this looks normal, but this is only at the side, and this is only on this corner. So it means that you have one free edge and that you have two other edges which are simply supported because of those torsional bending moments here in the corner.